Natalia, you are mute.
Yes. Yeah. Sorry. So can we start?
Yeah, I think we have all in now.
Okay, great. Good morning and good afternoon for everybody. My name is Natalia Taratuna, and I'm pleased to welcome you in the third day of our Early Career Researchers Workshop. The topic for today is recent advances in paleoclimate proxy indicators. The plan of our session is the same as yesterday. It's keynote speaker talk, questions from participants, and at the end there is a possibility for a short presentation of your data on this topic. Some words about our today's speaker. Let me introduce you Dr. Gabor Ujvari, a senior researcher at Research Center for Astronomy and Earth Sciences, Institute for Geological and Geochemical Research, Hungary. Major research interests of Dr. Ujvari are in quaternary geology and paleoclimate, low temperature, isotope geochemistry, and absolute radiometric dating of sedimentary rocks of the last 5 million years. So I stop my demonstration, and Dr. Ujvari, you are very welcome to start. Oh, you just unmute.
Yeah, okay. Now, can you hear me?
Yes.
Okay. Fine. Okay, can you see my presentation in full screen mode?
Yes.
It is working. Okay. Okay, thanks, Natalia, for the nice introduction. I would also like to thank the Chinese Association for Quaternary Research and also the Loess and Pedostratigraphy Working Group for inviting me to give this talk. That's a great honor to me, and hope you will enjoy my talk and you can follow my South Hungarian English pronunciation. Anyway, I should talk about recent advances in paleoclimate proxy indicators. First of all, I would like to clarify what is, in my view, the difference between the proxies and indicators of Loess. Is there any difference? I think there is. So I would like to talk about this. And then instead of speaking all these different proxies in Loess, I decided to highlight one and concentrate on carbonate climate isotope thermometry using lens navals. And this is why, because this proxy has seen a huge progress, I think, in the last couple of years. And of course, I would like to discuss all this in the light of traditional oxygen isotope thermometry of carbonates. So this will be shortly the presentations, which include actually 17 slides. So hopefully this will not be too long. This will fit in 40 minutes, of course. So all we are interested in Loess deposits, which are actually together with ice cores, paleothems, lake sediments, and marine sediments, are paleoclimate archives, which are important to us and important to actually provide any kind of useful information on past climate. What is a paleoclimate proxy, and is there any difference between an indicator and a proxy? And in my opinion, there is a difference, and these two must be distinguished. All we know that the meteorological measurements only started in the 1880s, or some decades later at some other places. So we don't have direct meteorological measurements of past climate in the Earth history. And this is why the paleoclimate proxies are important. Paleoclimate proxies are preserved physical or chemical characteristics of the past. Actually, in the case of Loess, the sediment itself, that stand in for direct meteorological measurements and enable scientists to reconstruct the climatic conditions over a longer fraction of the Earth history. So that's the definition. And it is quite clear that we actually need some kind of transfer functions to calculate quantitatively the different meteorological parameters from the physical and chemical characteristics of sediments or ice or any other paleoclimate archives. These meteorological parameters include, of course, the temperature, the rainfall, wind speed or wind directions, and so on. And let's see a list of different measured physical or chemical parameters in Loess. I actually listed only some, not all, what we can measure in Loess. The first one is magnetic susceptibility, which we know that it is an indicator of bacterial activity or soil development in Loess records. But this is also a proxy of rainfall because we have specific transfer functions, and using these transfer functions, we can quantify the amount of rainfall in the past. So this I consider a real proxy and not just an indicator. But what is the situation with the grain size composition, which we can measure using laser diffraction, or this situation of mass accumulation rates that we can calculate from the chronologies, absolute chronologies of these Loess records. These are integrated indicators, at least in my view, of wind strength, vegetation composition and type, and the nature of the alien surfaces, and the supply of these grains, and so on. So, many factors in the past. But at least to my knowledge, and again, in my view, this is not a proxy because we cannot quantify wind speed in the past. At least this is not possible at the moment. Maybe it will be in the future. So this is not a real proxy. It is just an indicator in my view. So, and the next one, major and trace element compositions and calculated indices like chemical index of alteration or ratios like rubidium, strontium, and so on. These are indicators of provenance. And to some extent, chemical weathering can be quantified, of course, using, for instance, the chemical index of alteration. And from modern soils, there were some attempts to use the potassium-free chemical index of alteration to calculate rainfall values. But these I consider actually a kind of semi-quantitative proxy at best. Other parameters are the rare earth element compositions, or strontium, neodymium, hafnium, lead isotopic compositions of the bulk sediment, or different fractions, or uranium lead age spectra of zircons or rutiles. And these are all indicators of provenance. This is not a proxy because provenance is not, first of all, provenance is not a meteorological parameter. And it is, I think, still at the moment, it is quite hard to quantify the different sources. And this is why I don't yet consider this as a proxy. But still, I would like to emphasize that provenance is very important to properly interpret any dust record coming from Loess records or coming from ice cores or any other archives, lake sediments. The next one I listed here is the carbon isotopic composition of the organic matter, which is an indicator of vegetation composition, the C3, C4 composition. Although this has been questioned in the last years, actually, recently. But this can be used, again, through transfer functions to calculate precipitation amounts in the past. And the last two, these are bacterial lipid-based indices like this MBT and CBT for the oxygen and clumped isotopic composition of carbonates. These are temperature proxies because we have proper calibrations for these. So in my view, this is the major difference between the proxy and the indicator, that the proxy means that we have specific transfer function and we can quantitatively reconstruct a specific meteorological parameter in the past. Okay, I mentioned previously that I would like to focus on carbonates, and I would like to show you some types of these carbonates in Loess. Like this first one, which is a tubular carbonate, formed around the roots of past vegetation. This is from a soil in Tajikistan from the Konako sequence. And the second example is a soil nodule, which is a very nice, pure nodule without any internal structure. This comes from the PC5 soil at Lakuti, also in Tajikistan. And there are also other forms of soil carbonates like these huge carbonates at the base of the MTP soil. This is MIS15 soil in the POX sequence in Hungary. These form petrocalcite layers at the base of this sequence. So this is another form of carbonate that can be used for the isotopic analysis. And of course, we have much smaller scale secondary carbonates in Loess, like these rhizolites, which are some millimeter in length. So these are actually quite small. And we have also biocarbonates in Loess, like these organonucleic shells of Succinella oblonga. This is from a Hungarian Loess sequence from the Nosecture. And also earthworms also produce granules in Loess, and this can be found especially in Europe, but potentially in China as well. I don't know for sure. This nice scanning electron image, which is from Olivier Moine and co-workers, published in PNAS, nicely demonstrate that these small-scale carbonates are actually made up of very pure calcite crystals. And the huge advantage of these two types of biominerals, shells and these ECGs, or earthworm-produced granules, is that they can be dated using radiocarbon, and we can provide high-resolution chronologies for Loess. That's the first thing that's huge, that has a huge importance. And of course, this can be subjected to oxygen or clamp isotope analysis. First, I would like to refresh your memories how to calculate temperatures from oxygen isotopes of carbonates. Oxygen has three stable isotopes, 16O, 17O, and 18O. And we are actually mostly interested in the 18O, 16O ratio, which is measured and expressed in the delta notation against the wheat PDB standard. But how to calculate temperature from the oxygen isotopic composition of these carbonates? For this, we need a fractionation equation between calcite and water. This can be, for instance, from Kim and O'Neill, which is actually a laboratory-based fractionation equation. But a better choice if we have a species-specific fractionation equation, like that one published by Versteeg in GCA for the earthworm granules. So if we have this fractionation equation, then we will also need an information on the oxygen isotopic composition of meteoric water. The major problem here is that we actually almost never know the oxygen isotopic composition of past precipitation, and it is really hard to calculate these values. I would like to demonstrate this double dependence of the oxygen isotopic composition of carbonates at the right-hand side in this figure. This shows actually the composition of carbonates as a function of temperature and the oxygen isotopic composition of the environmental water from which the carbonate precipitated. Let's take a degree of Celsius temperature. If we have an environmental water having 0 per mil oxygen isotopic composition, then we will have a carbonate of ±1 per mil. But if we have a much more negative oxygen isotopic composition of the water, then we will get a much more negative oxygen isotopic composition for the same carbonate formed at the same temperature. So this really nice to demonstrate that we have to know the oxygen isotopic composition of the meteoric water as well. There are some examples. A good one, for instance, can be in Prudhomme, who actually used the GNIP stations to calculate past meteoric water compositions. And this is actually one way out, but there are huge uncertainties associated with this approach. And I don't think this is the best one or the best choice at the present state of knowledge. So why to know the oxygen isotopic composition of meteoric water if we have another method which doesn't require this information, and this is lambda isotope geochemistry, which was introduced by John Ayler at Caltech and his team almost 20 years ago. We know that the traditional stable isotope geochemistry is concerned with the bulk isotopic composition, while the clumped isotope geochemistry is interested in how the various isotopes of carbon and oxygen are distributed in the crystal lattice of carbonates. You can see of different isotopologues of CO2 of the CO2 molecules at the right-hand side in this table with cardinal mass of 44 to 49. This 44 isotopologue of CO2 is the most abundant, and this is a so-called monoisotopic species, which means we have only light isotopes in the carbon dioxide molecules. With carbonate clumped isotope geochemistry, we are mostly interested in mass 47, the so-called doubly substituted clumped species, in which we have two heavy isotopes of carbon and oxygen. And this is actually the most abundant isotopologue with mass 47 is that one. The other two can be neglected during the measurements. And what is the basis of this clumped isotope geochemistry? We know that at low temperatures, molecules containing more than one heavy isotope are more stable than singly substituted species because of their lower zero-point energy. At high temperatures, about 1000 degrees of Celsius, thermodynamics drive the isotopic system towards a random distribution of heavy isotopes. While at lower temperatures, isotope clumping is more and more frequent between the heavy isotopes in our case of oxygen. And this other figure nicely shows the same. At high temperature, we have a few clumps. At low temperatures, we have actually more and more clumped species. So the abundance of the 13C and 18O bonds in carbonates are temperature dependent, and this is a good news because we can use this to calculate temperatures from carbonates in the past. Here I would like to again emphasize the difference between the traditional carbonate stable isotope thermometer and the carbonate clumped isotope thermometer. The first one, which is also called the Ujvari thermometer, because Harold Ujvari was the first one who suggested using this thermometer in 1947. So this thermometer examines a heterogeneous isotope exchange reaction between equilibrium between two phases, namely the calcium carbonate and, the calcium carbonate and the water from which the carbonate precipitated. So to calculate temperature, we need information, oxygen isotopic information from both phases. That's the problem with the traditional carbonate stable isotope thermometer. By contrast, the carbonate clumped isotope thermometer examines a homogeneous isotope exchange reaction, so the equilibrium among components of a single phase. And the single phase is the calcium carbonate, or rather the liberated CO2. And we are interested in this. And this reaction has an equilibrium constant, which is temperature dependent. It reaches 1 at high temperatures with a random distribution, and this is actually driven by configurant entropy in the system. At low temperatures, we have the lower vibrational energy of these mass 47 isotopologues. So we have more and more clumps, and this equilibrium constant will be lower and lower. So this is actually the basic of this method, and the clump isotope analysis measure the excess abundance of these 13C18O bonds based on measurements of the isotopologue of 47, dominantly 13C18O16O, compared to a stochastic distribution as it is written here. So that delta 47 equals to delta R47 divided R47 star minus 1. R47 is actually the ratio between mass 47 and mass 44 isotopologues. R40 star, the same, which is expected for a stochastic distribution. It's important to note here that the clumped isotope measurement results should be projected on the carbon dioxide equilibrium scale. This is also known as the absolute reference frame, which was introduced by Dennis and co-workers. And it's actually important for standardization and to make sure that the different measurements of different laboratories can be compared to each other. Because these empirical equations that use for these to create this absolute reference frame accounts for fragmentation and recombination reactions during the mass spectrometry. So that's important. And the latest carbon dioxide equilibrium scale is the so-called Intercarb C-90 scale published by Bernasconi, because it is now widespread to use different carbonate reference materials to provide standardization and normalization for the measured results of the different laboratories. These measurements require high precision and reproducibility, generally on the order of 0.05, 0.01 per mil, which can only be provided using specific instrumentation and specific laboratories. The measurements require about 2 5 milligram samples or more. This depends on the instrumental setup. And one temperature value with decent uncertainty requires 10-15 replicate analysis of the carbonates. So this is not easy, and it is a really time-consuming and meticulous work in the laboratory. To calculate temperatures from these delta 47 values, of course, we need calibrations for this thermometer. And I would like to show you only the latest calibration, which was published in Geophysical Research Letters in 2021 by Anderson and others. They call this a unified clumped isotope thermometer, which can be used between 0.5 and 1100 degrees of Celsius. And these authors used both natural carbonates and laboratory-grown carbonates to define these calibrations. And they also consider the different mineralogies like calcite, dolomite, calcite with minor aragonite to construct these calibration. And this is the latest published equation, calibration equation coming from this study, which can be used actually for calcite, and it is also can be used for the aragonite, at least based on these measurements. The question is, what is the situation with the mollusk shells? Because these are aragonictic shells, and we know that there are always some problems like vital effects with the mollusks. And Zarur and workers were the first one who studied the climate isotopic composition of multiple species from different environments with very different ecological demands. And they found that the mollusk shells actually precipitated and formed at climate isotopic equilibrium. And these calcification temperatures, which can be reconstructed from these delta 47 measurements, are usually higher than the activity season temperatures and the mean annual temperatures. And the temperature offset is lower and lower with increase in activity season temperatures. So this indicated that indeed the mollusk shells actually reflect the environmental temperatures, but these are usually higher than the mean annual values, and in many cases higher than the activity season temperatures. Later on, some 3 years or 2 years later, Eagle and others published another study in PNAS, and they reanalyzed some of the data published by Zarur for the monsoon regions, and they found that the calcification temperatures are higher than the summer average temperatures, and they are very close to the summer average high temperatures of that region of China. Then 3 years later, Wang et al. Published and reported results, delta 47 temperature results for Kataica and Brodibaena species from China. And they also found that these are higher than the growing season temperatures, and there is some degree of difference between these two species, which they attributed to the different activity seasons of these mollusks, with Kataica preferring the summer season and Brodibaena being more active during the spring and actually post-summer season. And this is why there is this difference. In 2018, Zhang et al. Published some results from laboratory experiments. So they actually didn't follow the previous approaches that used the natural populations of different land snails, but they kept these land snails at known temperatures in the laboratory. And they found and confirmed previous results that these shells form at climate isotope equilibrium, and they don't really show vital effects, at least in the laboratory. And the delta 47 values fit the delta 47 temperature calibration of Kelson, which was the latest calibration at that time. And this is a very good news, I think, for the use of mollusk shells to reconstruct temperatures in the past. Guo later on and others confirmed that these calcification temperatures are higher than the mean annual temperatures and close to the activity season. And Zai and others published further results from Brodibaena and Kataica, confirming previous observations of calcification temperatures being higher than the growing season temperatures, and they emphasize the need for species-specific transfer functions or calibration equations. The latest study I'm aware of was published 2 years ago in Chemical Geology by Dong and co-workers, and they studied multiple species, including Guanulia tenera, Pupilla aeoli, Kataica, and Brodibaena, and they found that the average temperature, which were reflected by the calcification temperature of these shells, were close to 28 degrees of Celsius ±5, which match quite well the average summer season temperatures of that region. We also started the calibration work here in Hungary using three different species, Succinella oblonga and Trochilus hispidus, for instance, which are widespread in loess deposits, at least in Europe. And we actually use different natural populations of these species, and also we started climate chamber experiments. Unfortunately, the measurements will only be done in September, the first measurements, so I cannot show you any results from this calibration. Instead of showing calibration data, what I said, they are not available at the moment, I would like to show you a case study which we started some years ago, and which actually a first attempt to use the fossil land snail shells of Trochilus hispidus and Succinella oblonga to reconstruct stadial interstadial temperature changes from loess in East Central Europe. And we actually also hope that we can get meaningful absolute temperature values from this sequence, which is actually the Loess ECR sequence. So Hungary is in the middle of Europe. This is called East Central Europe, and it is located at the southern part of the country, very close to Serbia and Croatia. And those loess sequences of Serbia, you may also know. This is close to the Danube River, so actually it is on the right bank of the river, and it has a very high resolution radiocarbon chronology with actually more than 125 measurements from the sequence in 5 centimeter resolution, at least for the upper part of the sequence. And we wanted to compare our reconstructed stadial interstadial temperature change values with flowstone, which is uranium thorium dated for 30 to 26 Ka. And this is from a nearby location. And we were really interested in the results. Here I show you the radiocarbon chronology of the two studied depth intervals of the Loess ECR sequence. We have many radiocarbon dates. There are some layers from which we have really multiple radiocarbon determinations from different target materials, including charcoals and mollusk shells. So this is a relatively well-defined chronology. And we were interested in GI 5.1, so the interstadial 5.1 and 3, and the surrounding stadials. And these are the results from these two species, Trochilus hispidus and Succinella oblonga. At the lower panels, you see the bulk mass accumulation rates calculated from the chronology. And we see two huge drops in the bulk mass accumulation rates, which actually match well these GI 5.1 and GI 3 phases. The match is not perfect, and this is first of all because of the chronological uncertainties. And here I would like to emphasize that we have an absolutely independent chronology from the North Grip ice core. And the North Grip ice core calcium record and the temperature records can be seen here in panel B and C. These two have independent chronologies, of course, and there are some uncertainties, and this is seen here. Panel F and E are the carbon and the oxygen isotopic composition measured in the snails, and panel D, which I would like to show you here, show actually the calcification temperatures of these shells, which we interpret as being the average, rather say average temperatures of the growing season from May to October. This we actually defined using the ecology of these snails. And yeah, if we look at the temperatures obtained for the stadials, like here, around these two interstadials, we see that these range between 7 and 13, 14 degrees of Celsius for the stadials, and the values are quite similar from both species, actually, like this one here, or this one here, or that one, after the GI3 phase. And this is really reassuring, and these stadial absolute temperature values are actually in very good agreement with other reconstructions from the region, and also with model simulations. Close to the GI3 phase, we see larger differences between the two species, and we attribute this to sampling issues. We sampled actually these two of the sequence in 5 centimeter resolution, which covers about 100 years. And we think that these two species actually represent a different living period of these snails, close to the interstadial. So low values representing the stadials, high values representing the interstadials. So in the future, I suggest actually who are interested in this technique to sample the Loess sequences at least around these stadial interstadial transition in very high resolution, for instance, in 1 centimeter resolution, to avoid any sampling issues. Anyway, compared to the stadial background temperatures, we see a marked increase in temperatures up to 16, 18 degrees of Celsius over these GI5-1 and GI3 phases. And this increase amounts to 4 to 7 degrees of Celsius. And it was interesting, we were interested to compare these values with delta T values, so temperature change values, reconstructed from the oxygen isotopic composition of this flowstone. For the flowstone, the oxygen isotopic compositions were converted to temperature change using these two 0.22 to 0.3 per mil delta 18O temperature gradients, which were calculated from GNIP stations of the region. And we see the same actually 4 to 7 degrees of Celsius temperature increase for the GI3 phase. And this comes from another archive, and I would like to emphasize the need for dual archive approaches, what we actually followed here, and this was also followed in some previous studies, what I have seen in China, that we should simply use different archives to confirm whether the reconstructed temperature changes are really real and valid. So I think carbonate clamped isotopes thermometry will see actually a huge progress in the future, and it provides actually a huge opportunity to use the widespread Loess deposits on the continents to reconstruct temperatures in the past. And I really hope that I will see many new studies in the future. And our study was only just the first one in reconstructed past temperatures from Loess deposits. If you are interested in the details, this was published in PP last year, so you can check these publications. And with this, I would like to thank you for your attention, and I would like to thank my co-workers who contributed to this study, because this was not my work. But they also contributed from the ETH and the colleagues at my institute. Thanks for your attention, and I'm prepared for your questions.
Thank you, Dr. Ujvari, and especially for your clarification between differences of paleoclimate indicator and proxies. Does anyone have any questions? Please feel free to ask them or just type it in the chat. I will read it, and you can raise also your hand in the Zoom and ask questions. Okay, maybe I can ask first.
Yeah, okay.
I would like to know, my sphere of interest is permafrost, and maybe you remember there are a lot of features of permafrost in Lower Volga region. We were there in 2018. So I would like to know, is it possible to calculate the temperature of the formation of these cryogenic features through the carbonates, different types of carbonates, then they precipitate from the solution?
Okay.
So
the question is what kind of secondary carbonates you have in your sequences. I don't know whether there are. Yeah. Okay.
And I can use to calculate the temperature.
I think at the moment we can use, for instance, soil carbonates to calculate temperatures. I didn't want to focus on the soil carbonates because this is another story. We also tried to use soil carbonates from Hungarian sequence, and we are working on carbonates from Tajikistan as well. So this is one secondary carbonate that can really be used to reconstruct temperatures, or the land snail shells. I have preliminary information on these earthworm produced granules. They don't look very good, at least based on the data what I have seen. But regarding your question, really the major issue here is what type of carbonate are present in your sequence, which would actually form at the same time as your I don't know, veg or something like that from the permafrost. So this is the issue here, whether these two are contemporaneous or not. And then I think there is a good chance to reconstruct temperatures from the permafrost as well.
Okay. Thank you. I see that Viktor Rogov would like to ask something.
Yeah, okay.
Наташенька, спроси, о какой температуре идет речь? Воздуха, воды, в которой живут эти организмы, грунта или еще что-нибудь? О какой температуре идет речь?
Professor Rogov are asking about which temperature is for, I don't know, living of these shells, mollusks.
Yeah. Okay. So I think it's important to know that what is the ecological demands of this different species, and this is the first step to properly interpret such kind of temperature data. The second one is, and the best way of doing this research is that one have to calibrate these equations and the different snails using clumped isotope measurements of natural populations, because that way you can actually have information on the living conditions of your natural populations. This can be, this kind of information collected from meteorological stations, and then this can be compared to the gasification temperatures reconstructed from the Delta 47 measurements of the natural population. So using this, you will have a robust understanding of the vital effects what are present. Usually, actually, these species reflect the growing season temperatures or activity season temperatures, or even higher temperatures, because in some cases, the species are active during actually only the summer. But again, this depends on the ecology of the specific species. And these are sometimes active during the night and not during the day. And these are active after large amounts of precipitation. So that has to bear in mind. So and also this must be somehow accounted for in your reconstructions. So in our case, in short, the temperatures were, at least we think, were close to the growing season temperatures, but we were not absolutely sure about this, and we couldn't quantify the vital effects. This is why we started these measurements on the cultured populations in the laboratory and natural populations across Europe. So that's the only solution, I think.
Okay, thank
Thank you very much for
You're
your
welcome.
report.
Does anyone have any questions? Okay, we have reply in the chat.
Okay, I can read it.
Yeah.
Okay, yeah, that's a very good question actually, because there are of course limitations. I mentioned that we don't need extra information on the oxygen isotopic composition of the formation water, which is a huge advantage of this technique. But we have to know that to get a meaningful average temperature, we have to analyze at least 10-15 replicates, and then we will have temperature uncertainty on our average value of about 2 to 4 degrees of Celsius. So this is one limitation, of course, because this method has some uncertainties. Also, the other issue is potentially the diagenetic effects for instance, Loess records in deep time, because we could potentially go back to millions of years using Loess deposits in China or Tajikistan or at other places on Earth. And that's true because that will change, of course, or potentially change the temperature value, what we reconstruct from our record, actually. The major, I think, what we can do here first, that we should check the composition, the mineralogical composition, first of all, of these shells. This can be done using Fourier transform spectrometry, FTIR, infrared spectrometry. So we can confirm that these shells are orgonitic, and these shells are not converted to calcite, because that may cause an isotopic exchange, or this may influence our temperature value, what we will reconstruct. So that's an important thing what we should do, I think. Yeah, and another issue, the vital effects again. I haven't mentioned that this technique actually was expanded in the last years, because not just the delta 47, but delta 48 can also be measured using these spectrometers, and we can calculate temperatures combined from the delta 47 and delta 48 values, and this way potentially we can quantify the vital effects from these shells, which can also be a limitation of our method, because on one hand we can calculate relative temperature changes without having any species-specific equations, but to calculate absolute temperatures we will need the calibration equations, and using calibration equations we can avoid the effect of these vital effects, actually. I hope I could answer your question. Thanks again.
Thank you, Lily, for your question. Okay, so maybe someone would like to present their data and discuss it with the community and with Gabor, because nobody applied for it, but maybe now someone would like to do it.
If not now, no problem. Then you can contact me anytime. So that's no problem. Just drop me an email and I will certainly answer this email. So I'm very open to any cooperation and any suggestion what you have.
Gabor, there is another question in the chat.
Okay, yeah. Is it possible to apply clamp isotopes to soft and diffuse carbonate concretions that are common in soils? I tried clamp isotope thermometry only once from an MIS5 soil from this Loess ECR sequence. This was published in PPP or P3 2019. So you can check that publication, but my answer is that I would go for nice carbonates, which should be pure actually. You will of course not find extremely pure carbonates. This will also always be contaminated with some clay minerals and so on, but this doesn't really matter. I'm a bit more cautious, or would be a bit more cautious with diffuse carbonates, which are just actually carbonates which cemented material or soil material. I'm not sure that this can be used for the clamp isotope measurements, but I don't know because I have never tried it. So my message here is that I would go for the intact carbonates as much as possible. You can use carbonates from the petrocalcite layer below or at the base of the soils. You can use these different types of soil nodules without real internal structures. But it's important for the carbonates, and I say this because of previous work in the literature, that you should collect that part of the carbonate which comes from a specific carbonate mineralogy and structure of this mineralogy. We always like to collect samples from the micritic carbonates because this way you can make sure that this will be a primary signal what you measure. So that's my short answer.
May I ask something else here?
Yeah, of course.
That's true.
For example, if the carbonate has a central part which is a nodule, and the outside is like soft and diffuse, would it affect? Yeah. For example, if I would try to work with the nodal part, which is hard, would the outside affect the results of the analysis?
I see a low chance for this. I mean that the internal part would be affected by this diffuse part. So I would certainly use the internal part of the concretion. Just you should actually somehow calculate the period of formation of this carbonate, which can actually be done if you know the age of the soil and so on. So. But still, I think you can get useful information from the internal part of that concretion. So just go for it.
Okay. Thank you.
You're welcome.
Thank you. So, any other questions? Yes, another one.
Yeah. Okay, I will read it. I will ask another one if we have time, of course, of the various chemical weathering indices, with varying advantages, limitations. Just curious, which are your preferred proxy for evaluating rainfall chemical weathering in Loess paleo soil? I actually used both the chemical index of alteration and chemical index of weathering. Or you can use the CPA by Google and others, which is actually not much different from previous chemical indicators. Using chemical index of alteration, you can really quantify the chemical weathering or silicate weathering in your sequence. So I would prefer using chemical index of alteration or weathering. So this is both can be used, I think, and I suggest using the rubidium strontium, barium strontium ratios, for instance. But on the other hand, I don't really like using these different indices to calculate rainfall values, because as I mentioned in my talk at the beginning, that I consider this only a semi-quantitative proxy. If you check the results based on these transfer functions are calculated, then you realize that there will be huge uncertainties on your calculations. I don't state that these are useless, of course, these are useful, but I would never calculate rainfall based on these transfer functions using, for instance, potassium-free chemical index of alteration.
Thank you. Thank you. So, as I understand, everybody can contact with you if they have other questions. So, you're welcome. I would like to close the discussion, and thank you very much, Dr. Ujvari, for your time, for sharing your knowledge with us, and thanks to all participants who asked questions, who listened to you. So thank you very much. Goodbye.
Yeah, I would like to also thank you for your interest. Yeah.
Thank you.
Thank you, Gabor. Very nice talk. Thank you.
Thanks.
Thank you.
Bye.